The enigmatic depths of our solar system have recently yielded a captivating discovery. A mysterious interstellar visitor. Traveling from the distant reaches of another star system, this object has been designated by astronomers as 3I/Atlas. The very presence of such an interloper raises profound questions. Is this merely a conventional comet, a chunk of primordial ice and rock ejected from its native system? Or, as proposed by the highly controversial but nonetheless prominent astrophysicist Avi Loeb of Harvard University, could it be a controlled, operational vessel or, perhaps, debris from an extraterrestrial civilization? Furthermore, is there a risk or a deliberate plan for this enigmatic object to intersect with our own planet, Earth? These questions thrust us into the realm of astronomical detection, orbital mechanics, and the search for life beyond our world. This detailed exploration transcends the ordinary, venturing into the cutting edge of astrodynamics and scientific speculation. The advent of 3I/Atlas, the third interstellar guest. The appearance of any foreign interstellar object, ISO, in our solar system invariably generates a surge of excitement and debate within the scientific community. 3I/Atlas, officially designated as C/2023 A3 Atlas, is the third confirmed interstellar object to be identified, following 1I/Oumuamua and 2I/Borisov. For American astrophysicist Avi Loeb, known for his penchant for interpreting astronomical anomalies through the lens of extraterrestrial technology, each new ISO arrival is the basis for a new chapter in a grand cosmic detective novel. The third confirmed interstellar object was officially catalogued on July 1, 2025, though the discovery date in the original text of July 1, 2025, seems to be a speculative date. We will proceed with the narrative as provided, maintaining the sequence of events as described. What makes this third object, 3I/Atlas, particularly noteworthy? Discovery and distant behavior. Firstly, and quite unusually for a cometary object, 3I/Atlas was discovered relatively far from the Sun, roughly near the orbit of Jupiter or even slightly beyond. Comets, in general, are reluctant to display their characteristic tails and comas at such distances, as the frigid temperatures prevent the volatile ices from sublimating, the process that forms the observable cometary atmosphere and tail. If 3I/Atlas is indeed a comet, this distant visibility suggests it must be of a considerable size. A large body would reflect sufficient sunlight to be detectable by telescopes even at great distance. Under this assumption, the solid nucleus of the object might be estimated to be approximately 20 kilometers in diameter. The ambiguity of the tail. Secondly, a peculiarity surrounding the object is the structure tentatively identified as a cometary tail. Avi Loeb and his collaborating English colleagues published a paper highlighting that this observed tail might not be a natural cometary feature at all. There is a possibility that the observed feature is a mere photographic artifact, a slight smearing or elongation of the image due to the object's rapid motion relative to the telescope's tracking, a common effect in deep sky photography. If it is a genuine tail, it confirms the object's cometary nature, indicating sublimation. However, if the feature is indeed artificial or an observational error, the core mystery deepens. Size estimation. Coma versus core. The true physical size of the object remains a significant unknown. If 3I/Atlas is not a comet, the sheer amount of reflected sunlight needed to make it visible at Jupiter's orbit suggests a substantial solid body, potentially up to 20 kilometers in diameter. Conversely, if it is a comet and has already begun to heat up and vaporize, it would surround its solid nucleus with a temporary atmosphere called a coma. This gaseous cloud dramatically increases the object's effective reflective surface area, making the entire structure appear much larger. In this cometary scenario, the solid, rocky nucleus could be much smaller, possibly only 1 to 2 kilometers across. Until the object approaches the inner solar system and allows for high-resolution imaging, this ambiguity will persist. The alarming orbital characteristics. The main factors that triggered the extraordinary claim of an artificial origin, the fantastical element, as the text describes it, lie in the object's orbital mechanics. The specific characteristics of 3I/Atlas's trajectory present a statistical improbability that has fueled the speculation of a directed path. 1. Ecliptic plane alignment. The most striking feature is the orientation of 3I/Atlas's orbit. Its plane of motion is nearly coincident with the plane of the solar system's planets, known as the ecliptic plane. All major planets, including Earth, orbit the Sun in this relatively flat disk. For an object randomly ejected from a distant stellar system, its trajectory relative to our solar system should be purely arbitrary, arriving from any direction in three-dimensional space with equal probability. The fact that 3I/Atlas entered the system at an angle of approximately 5 degrees relative to the ecliptic plane is statistically unlikely for a naturally scattered object. While Loeb and his colleagues initially calculated the probability of such an alignment at less than 1%, a more conservative estimate suggests a probability around 5% to 6%. Even this higher figure represents a low probability, suggesting that the object wants to interact with the solar system's planetary environment. 2. Retrograde motion. The second unusual feature is the direction of its orbital motion. All planets in the solar system, as well as the Sun itself, orbit and rotate in the same direction, counterclockwise when viewed from the North Pole. This is a remnant of the angular momentum of the initial protoplanetary disk. 3I/Atlas is traveling in a retrograde orbit. It is moving clockwise, flying head-on into the traffic flow of the planets. In isolation, the probability of an interstellar object having a prograde, forward, or retrograde, backward, motion is an equal 50%. This characteristic alone is not strange. However, when combined with the near-ecliptic alignment, the likelihood of a randomly scattered object having both these properties simultaneously becomes extremely small. The combination suggests that the body did not simply fall in randomly from the chaotic stellar environment but was somehow guided or ejected along a predetermined path relative to our planetary disk. The interstellar rendezvous and gravitational maneuvers. The controlled craft hypothesis gains its strongest support from the predicted path of 3I/Atlas. Astrophysicists, citing the object's high speed, around 60 kilometers per second, have calculated a series of remarkably close flybys with 3 major planets. In the crucial period of August, September, and October, the object was predicted to execute close passes near Jupiter and Mars. The flyby of Jupiter, a massive body, offers the first significant opportunity for trajectory alteration. The subsequent pass near Mars is predicted to be exceptionally close enough, perhaps, for the orbiters currently operating around the red planet to capture high-resolution images. The crucial speculative step is the possibility of a gravitational assist or slingshot maneuver. If the object is indeed artificial and controlled, it could use the gravitational fields of the planets it passes to alter its future course. By timing its flyby of Jupiter and Mars precisely, the object could position itself for a decisive maneuver near Venus. A gravity assist from a planet can be used not only to accelerate a spacecraft, as famously done by Voyager, but also to decelerate it. This technique is routinely used by Earth-built probes. For instance, the Parker Solar Probe executed multiple flybys of Venus to shed orbital energy and dive closer to the Sun's inner corona. The deceleration plan. If 3I/Atlas executes the requisite maneuvers, decelerating at the precise moment by using Venus's gravity, it would accomplish a nearly impossible feat for a natural ISO. It would not escape the solar system like Oumuamua and Borisov. Instead, it would slow down sufficiently to enter a long-term, stable, sun-centric orbit, effectively becoming a permanent resident of our system. Why would an extraterrestrial vessel attempt this? The trajectory, if managed successfully, could culminate in 2 objectives. 1, proximal solar orbit, to approach the Sun closely, perhaps to conduct research on solar dynamics or, as Loeb speculated for Oumuamua, to refuel or recharge its power systems via solar radiation collectors. 2, Earth rendezvous. By remaining on the ecliptic plane and managing its orbital velocity, the artificial object could set a course for a close approach with Earth. This scenario, however fantastic, directly invokes concepts from famous science fiction. The authors of the analytical paper themselves immediately referenced Liu Cixin's The Dark Forest, a Chinese science fiction novel that suggests any known alien civilization is immediately a target for destruction by others, leading to a profound silence. If 3I/Atlas is a probe, its discrete approach and potential masquerade as a comet could be a tactic to remain hidden. This ties into the Fermi paradox, the contradiction between the high probability of extraterrestrial civilizations and the lack of observable evidence, by suggesting they are here but are deliberately concealed. The predicted close approach to Earth, if the trajectory adjustments are executed, is estimated to occur around late November or early December of the current year, as per the podcast's timeline. The scientific versus didactic purpose. Avi Loeb and his collaborators have stated that their paper is partly a didactic exercise, a demonstration of how astronomers could calculate the potential trajectory and behavior of an artificial interstellar object. It is a framework for looking at ISOs not merely as chunks of rock, but as potentially engineered systems capable of non-gravitational maneuvers. However, a good academic exercise could also turn out to be a correct strategy employed by an interstellar probe. The coming weeks of observation, focusing on whether the object continues on its predetermined, unmanaged path or begins to display non-gravitational acceleration indicative of a maneuver, will be crucial. The cometary masquerade, an extraterrestrial tactic? The final, highly speculative element is the possibility of the object actively disguising itself. If 3I/Atlas is indeed a controlled craft, could it be intentionally mimicking a comet? A spacecraft possesses the capability to generate a gaseous envelope, or coma, around itself. It could release dust and gas to create a temporary tail, effectively putting up a smokescreen or a military deception tactic to appear as a harmless, natural celestial body. This possibility demands painstaking analysis of the object's chemical composition and the characteristics of its tail. If the emissions are non-standard for a solar system comet, say unusual ratios of carbon compounds or a lack of the expected water ice sublimation, it could point towards an artificial origin. The precedent, Oumuamua 1I, and its mysteries, 3I/Atlas, is only the latest in a series of strange interstellar visitors. Avi Loeb's suspicion of extraterrestrial origin is not new. It was crystallized by the first ever confirmed ISO, 1I/Oumuamua, which transited our system in 2017. Oumuamua, a Hawaiian term meaning a messenger from afar, immediately presented several profound enigmas that set the stage for the current debate. The problem of velocity and origin. The confirmation that Oumuamua was an interstellar object rested on its hyperbolic trajectory and extreme velocity. An object belonging to the solar system is gravitationally bound to the Sun and moves at speeds that allow it to remain in orbit. An object approaching from another star system, however, can enter with high, peculiar velocity, and the Sun's gravity is insufficient to capture it. Oumuamua was moving so fast that it was guaranteed to pass through the system and return to the interstellar void. Its arrival was detected late. It was only noticed after it had passed closest to the Sun and was already on its outbound leg, having flown in from a direction close to the Sun that makes astronomical observation difficult. This late detection made studying it extremely challenging. The shape, the cigar/pancake anomaly. What astronomers did manage to glean was remarkable. Oumuamua was estimated to be hundreds of meters long but only tens of meters thick. This highly elongated shape, variously described as cigar-like or a flat pancake, was entirely unprecedented. Among the nearly 2 million asteroids discovered in our solar system, none possess such a high aspect ratio. To have the first ever interstellar visitor exhibit such a bizarre, non-spherical, almost deliberately streamlined shape was a major statistical anomaly. Loeb seized on this, noting that such a shape is reminiscent of what science fiction portrays as a mothership, or, more practically, an interstellar probe designed to minimize drag and stress. The unexplained acceleration. The most controversial feature of Oumuamua was its motion after passing the Sun. As it sped away, astronomers noticed a slight but measurable non-gravitational acceleration. It was moving slightly faster than could be accounted for by the Sun's gravity alone. In a natural scenario, this is the classic signature of a comet. As the Sun's heat causes ice to sublimate, jets of gas erupt from the nucleus, acting like small rocket thrusters and pushing the comet forward. However, the sensitive telescopes used to observe Oumuamua detected absolutely no cometary outgassing, no tail, and no coma. It appeared to be an inert rock, yet it was accelerating. Alternative natural theories. To explain the acceleration without a visible tail, natural hypotheses were proposed. Hydrogen ice. It was suggested Oumuamua might be made of pure hydrogen ice, H2 H_2H2, which would sublimate invisibly in the vacuum. However, H2 H_2H2 ice would evaporate so rapidly during its long transit through interstellar space that an object of Oumuamua's size would never have survived to reach our solar system. A nitrogen ice. Another theory proposed it was a chunk of solid nitrogen, perhaps a fragment of a planet like Pluto from another system. This could explain the acceleration without a visible tail, but it still requires a complex, unlikely formation history and a specific mass loss rate. Loeb's solar sail hypothesis. Avi Loeb rejected all natural explanations as too contrived and statistically improbable to account for the totality of the anomalies. His proposed explanation: Oumuamua was accelerated by solar radiation pressure. Light exerts a tiny but continuous pressure on any surface. For this pressure to cause the observed acceleration, the object must have an extremely low mass density relative to its surface area. Loeb argued that Oumuamua was not a solid rock but an incredibly thin, large, lightweight structure, in essence a solar sail or perhaps a thin-walled, hollow piece of technological debris. This structure, whether functional or derelict, would fit the observed shape, the density requirement, and the non-gravitational acceleration without the need for visible outgassing. Furthermore, Loeb noted that Oumuamua's trajectory brought it close to the Sun's inner orbit, closer than Mercury, but avoided an incineration by solar rays, a carefully calculated path, perhaps designed to charge up its power source via its massive surface area before departing. This suggested a deliberate reconnaissance mission. Comet Borisov, 2I, the baseline of normality, the second interstellar object 2I/Borisov, discovered in 2019 by amateur astronomer Gennady Borisov, a staff member at the Sternberg Astronomical Institute, provided a crucial counterpoint to Oumuamua and a baseline for comparison. Borisov was a definitive, textbook interstellar comet. It possessed a clear coma and tail. Its motion was consistent with cometary outgassing, though also showing some non-gravitational effects, common for comets, and its spectroscopic analysis confirmed the presence of volatile compounds consistent with cometary ice. 2I/Borisov's appearance allowed astronomers to confidently say, "This is what a natural interstellar comet looks like." It confirmed that a substantial fraction of the interstellar medium is populated by natural cometary material ejected from other star systems. But it did nothing to resolve the mystery of the preceding object, Oumuamua. The subsequent long period without a discovery, nearly 6 years between Borisov and the speculative date of 3I/Atlas's discovery, was a point of contention, as theoretical models suggest new ISOs should be entering the system approximately every 1 or 2 years. This period underscored the incompleteness of our sky monitoring infrastructure. The interstellar meteor IM-1 and the deep-sea expedition. Avi Loeb's pursuit of extraterrestrial artifacts did not end with Oumuamua. Driven by the theory that these objects must be common, he sought evidence that they had impacted Earth in the past. Discovery via meteor patrols. Loeb meticulously analyzed data from global meteor patrols, networks of cameras and sensors originally designed to track meteors entering Earth's atmosphere. When a meteor is tracked by multiple, distant sensors, its trajectory and speed can be calculated in 3 dimensions. Loeb focused on high-velocity objects. As previously established, an object traveling at an extremely high velocity cannot be gravitationally bound to the Sun. If it's fast enough, it must be an ISO. Through this deep search, he identified one specific meteor track, dubbed IM-1, Interstellar Meteor 1, which demonstrated a velocity so great that its interstellar origin was considered highly probable. This event had occurred years prior, in 2014, over the Pacific Ocean near Papua New Guinea. The expedition to the ocean floor. Based on the trajectory data, Loeb calculated the general impact zone of IM-1's remnants in the Indian Ocean. He successfully secured funding and chartered a ship equipped with a magnetic dredge, embarking on a remarkable expedition. The objective was to recover metallic spherules, tiny, melted droplets of metal that are vaporized from the surface of a meteor as it ablates, burns up, during its high-speed entry into the atmosphere. These droplets cool and fall to the ocean floor along the meteor's flight path. Loeb hypothesized that if the object was a natural, fast-moving interstellar meteor, its composition would differ from solar system rocks, reflecting the different metallicity of its parent star system. If it was an artificial object, the metallic spherules might display elements or alloys indicative of engineering. The anomalous composition. The expedition successfully retrieved hundreds of microscopic metallic spherules. Analysis of their composition revealed an anomaly, particularly an excess concentration of heavy elements such as beryllium, Be, lanthanum, La, and uranium, U, a signature sometimes referred to as the Ballah anomaly. Loeb argues that this particular combination and abundance is unique, distinct from all known solar system meteorites, thus confirming the object's extrasolar origin. While not all meteoritic specialists agree, some caution that similar compositions, while rare, can exist in terrestrial or natural meteoritic materials. Loeb maintains that the spherule's unique makeup points to an origin in a different planetary system with a different element formation history, or potentially that the metal alloy was deliberately engineered. This bold initiative, moving from theoretical astrophysics to deep-sea recovery, epitomizes the aggressive, boundary-pushing approach that Loeb has brought to the hunt for extraterrestrial artifacts. The future of interstellar object discovery. The current era of ISO discovery is one of extreme rarity, but this is set to change dramatically in the coming years. The LSST revolution. The key to unlocking the true frequency and diversity of interstellar objects is the Vera C. Rubin Observatory, currently under construction in Chile. This facility, equipped with the massive Legacy Survey of Space and Time, LSST camera, is designed to survey the entire visible sky every few nights with unprecedented depth and sensitivity. When LSST becomes operational, astronomers anticipate a dramatic increase in the rate of ISO detection. Instead of seeing one object every few years, the models suggest the LSST could find dozens, if not hundreds, of new interstellar objects annually. This influx of data will transform the field. With a large sample size, astronomers will be able to 1. Statistically validate, determine the true statistical frequency of Oumuamua-like objects versus Borisov-like objects. Are elongated, tailless objects like One-Eye truly rare, or just the most extreme example of a common new class of ISO? 2. Characterize orbits. Analyze the distribution of orbital planes and velocities to understand if the near-ecliptic alignment of 3I/Atlas is a genuine anomaly or a statistical quirk of small numbers. 3. Prompt missions. The early detection of new ISOs will allow for the rapid planning and launch of dedicated intercept missions, something impossible for Oumuamua, which was detected too late. The ability to intercept and land a probe on an interstellar object is the ultimate goal, providing irrefutable evidence of its composition, be it rock, ice, or metal. The shifting paradigm. The work of Avi Loeb and the appearance of objects like Oumuamua and 3I/Atlas are forcing a paradigm shift in astronomy. The default assumption for any newly discovered object is that it is a natural phenomenon. However, the rigor applied by Loeb suggests that for a scientific hypothesis to be complete, the possibility of an artificial origin, the technosignature approach, must be considered, analyzed, and statistically ruled out before settling on the most exotic natural explanation. The coming decades promise a new chapter in the search for extraterrestrial intelligence, SETI, moving from passive listening for radio signals to the active, physical examination of objects that have literally arrived on our cosmic doorstep. The discovery of 3I/Atlas serves as an urgent reminder that the universe is actively sending us messages, and it is up to us to refine our techniques, set aside our prejudices, and be prepared to read them.